Okay, thank you. Thank you very much. And thank you, Bernard. Uh, I'm going to talk about this related question with the program we've been working with Benito Juarez, Bernard Kay, and Daniel Sudarsky. And I'm going to be focusing on the problem of the notion of a Hadamard state within Cauchy hypersurface in the context of semiclassical gravity. So we will need to do a approximate notion of Hadamard state. This is a more conceptual talk than the one that a more technical talk than from Bernard. Uh, I'm going to be focusing on some technical aspects of this approximation. I'm going to quickly recall the semi-classical gravity scheme we are working with. So we will deal with the semi-classical Einstein equation, which we have already seen a lot of times in this workshop. And essentially, we're treating the Einstein-Klein-Gordon system, which consists of besides of the Einstein-Klein-Gordon Einstein equation with the expectation value of quantum field given by the star algebra generated by some field acting on test functions that satisfy these canonical relations, right? This is quite standard, and the particular thing about semi-classical gravity is that we need to sort a particular state that satisfies the semi-classical Einstein equation. For that, we need to be able to determine the expectation value of the energy momentum tensor, which is not easy to do within the standard formulation of the quantum field theory, and we require a renormalization procedure for that. Fortunately, we can restrict ourselves to Hadamard states, which will allow us to compute the expectation value by a very explicit and straightforward prescription, where we will see that in fixed spacetimes, you define the Hadamard condition in terms of the singularity structure of the distributional kernel of the point functions of the state, which has to be of this particular form with the divergent term that goes like 1 over the squared geodesic distance, which is this part with the u, and a part that goes like the logarithm of the geodesic distance, the squared geodesic distance, which is this part that goes with v. And then we express that the two-point function has can be split in that singular part and the smooth regular part w. Here u and v are bi-scalar functions, regular, and the coincidence limit of x prime goes to x. Well, in general, we can solve these functions like making an expansion and a power series in the squared geodesic distance. Actually, sigma is half the squared geodesic distance, and that allows to compute a set of differential equations for each coefficient at each order. And the interesting thing there is that the functions u and v do not depend on the state, while the part that we have called w encodes the information on the quantum state, right? So far, this is quite standard. And then the renormalization of the energy momentum tensor can be done by applying a differential operator, here represented by curly t, acting on the regularized point function. That is in this case, the Whitman function subtracted the Hadamard singular part. And actually there is a need to subtract the part that violates the energy momentum conservation, and therefore to recover consistency with the semiclassical Einstein equation, and in particular with the Bianchi identity, we need to subtract this term that includes the one of the coefficients of the bi-scalar v in the Hadamard form, and we are using the results from the Caninian Fibonacci here explicitly that have already computed this, out of this has been computed previously, and just here I want to highlight that these introduce higher order terms. That means derivatives of the curvature that render the system fourth order in the derivatives of the metric. We can also add an ambiguity term here represented by theta, which is a locally conserved term constructed out of the curvature, but we cannot use that term to cancel the higher order terms of the renormalized energy momentum tensor. So that's why we cannot reduce this problem to lower order system, and therefore we cannot use the classical proof for the initial value problem of general relativity to establish that there's a single Cauchy development for given initial data. In this case, when we want to go in the semiclassical gravity regime, that is, the space-time is no longer fixed nor given, we cannot even specify the Hadamard condition if we don't have the available the whole space-time, or at least information on the neighborhood of a Cauchy surface. And in particular, we should note that if we only have information of the metric in a given surface, maybe the extrinsic curvature, we cannot directly specify what is the geodesic that connects points within the same hypersurface, because the geodesics will, in general, lie outside of a given hypersurface. So, what we are going to do to overcome this technical aspect is to assume there is a set of finite initial data that allows to reconstruct the complete semiclassical solution given in a initial Cauchy hypersurface. And this is only like a working hypothesis. Once we have that, we can formulate the Hadamard condition in as before, assuming that we have the necessary elements to define this object, and we can compute the Hadamard condition in terms of initial data, that is projecting and putting everything in terms of the of data over the Cauchy hypersurface using the 3+1 formalism, for example. Okay. Yes. So, concretely, this means that we can take 3 steps for determining which is the necessary initial data for establishing the Hadamard condition on a Cauchy hypersurface. We will assume that with such initial data we can construct approximations for the square geodesic distance and the scalars u and v. Then we need to compute how good these approximations have to be, and that's what we are going to compute in much of the remaining of this talk in terms of derivatives of the coincidence limit of the derivatives of say approximations in relation to the exact or complete functions they try to approximate, and then actually computing these approximations. Well, for the geodesic distance square, we will require that it at least satisfies the first two derivatives, so that the limit of the first two derivatives of the approximation match those of the actual space-time geodesic distance. With that, we can define the approximations for the bi-scalars v and u in the same way as it's usually done when we formulated the Hadamard recursion relations. That is taking v to be approximated by a power series in the square geodesic distance, although we will use the approximated version, and then each coefficient will be expanded as a covariant Taylor series, but modified to use the approximated expansion of the geodesic distance. Then the coincidence limits of the approximation will be given by the coefficients, and if we make them to match those of the actual exact bi-scalar v, we see that the coefficients will be the same of the covariant Taylor series for v. And the history for u is essentially the same, although we don't need to do the power expansion in first place, because that series truncates at the first term, and leading to the what is called the Van Vleck-Moret determinant, and therefore we only require to expand it in the covariant Taylor series, where again the coefficients will coincide with the exact coefficients from the original bi-scalar u. Okay, so we finally can construct with all these elements an approximate Hadamard piece, subtraction piece, which I simplify here, and we define then these kind of error functions that measure how or approximations fail to satisfy or to match the exact bi-scalars we are trying to reproduce, and we impose a condition on the error we commit in the approximation for the Hadamard subtraction piece. Given that the higher order derivative acting on the term, on the regularized term of the point function in the energy momentum tensor prescription is a second order derivative, we require that the limit of said derivatives vanish. This has some technical aspects that this can be put a little more formally, but in general, this is the basic condition. Then by using this Sinch formula, we can actually expand to obtain the remaining terms that we are missing here, and we impose that condition on each one of them. But essentially, it's the same computation. So what we do now is to fix a set of coordinate chart and work with the coordinate component. This is there is an error here in this. It should be mu and nu, implying that we are working with the components of the derivatives of the error function for the Hadamard form, and express that in terms of the original functions and their errors. So we obtain an expression like this, where I will then see what is the curly white. But here we can see already that we need at least a first order approximation for the geodesic distance squared. So to make this first term to vanish, and second order approximation for the bi-scalar v, so that the last part of this function vanishes. Otherwise, we will have a divergence here. The term that I only called y curly is actually all of these terms that I don't expect anybody to review explicitly, but to just note that here is a part missing. That if the approximation is such that at least the third order derivatives of the geodesic distance vanishes, the complete term vanishes. Here there is missing a part that goes like sigma to the 6th power, but seems like well, it was rather relevant to be shown that here. But the point is that you can apply then the L'Hopital rule, which is not seen here because it's called down for some reason. And you can apply the L'Hopital rule in a very particular manner several times to recover a finite limit. In order to do that, we have to choose a direction where we do the derivation procedure, and so we use this notation for the directional derivatives, obtaining that we need at least 6 vanishing directional derivatives for the geodesic distance, the squared, and 4 directional derivatives for the scalar u, and 2 directional derivatives for the scalar b. Okay, so the issue is that we can use we can exchange these directional arbitrary covariant derivatives by the derivatives associated with the induced metric in the hypersurface, and therefore we only need 6 order derivatives, tangent derivatives for the geodesic distance, or 5 tangent derivatives for covariant derivative of the geodesic distance, and 4th order tangent derivatives for the second order covariant derivative of the geodesic distance. Those are the terms corresponding to the first line here. Yeah. So the issue we are approaching is that we cannot take derivatives of something like the intrinsic geodesic distance. So we will propose the spacetime geodesic distance to be a square geodesic distance to be approximated by the half the square geodesic distance on the hypersurface. But we cannot take derivatives of said thing because it's only defined for points within the same Cauchy hypersurface, and therefore we cannot take any normal derivatives for that object. However, we can define the time derivatives or normal derivatives as an independent series that do not involve any sort of derivation on sigma, and the coefficients are computed by requiring their coincidence limits to coincide with those of the derivatives of the geodesic distance in the corresponding geodesic distance. Okay, so we can compute those coefficients just like it's done for the Taylor and the standard Taylor series. Although we have to project the corresponding limits in the 3+1 formalism and express everything in terms of the induced metric on the hypersurface and the extrinsic curvature and its derivatives. So this is what we obtain for the half the square geodesic distance, and it's up to the 6th order where we find a normal derivative of k. That we can remember that k, the extrinsic curvature, is a derivative already of the intrinsic metric, the induced metric on the hypersurface, and therefore this represents a second order derivative of the metric. We can actually rewrite the first 5 terms here using an identity satisfied by the half the square geodesic distance in this term. So at first order, the space-time geodesic distance goes like the intrinsic geodesic distance, and then we have to use the extrinsic curvature to compute corrections for the geodesic space-time geodesic distance. Well, then for the normal derivatives of the special geodesic distance, space-time geodesic distance, we obtain that again we only require a first order normal derivatives of the extrinsic curvature. Therefore, again, second order in the metric, and only when we take 2 derivatives in the normal direction is that we need a second order derivative of the extrinsic curvature or a third order term for the metric. However, for the terms that we already mentioned before, the 4th order coefficient of the scalar u actually includes a 3rd order extrinsic curvature derivative. So in the normal direction, here I forgot to mention that this t with a bar means simply derivative in the normal direction, and the scalar already includes again 4th order derivatives of the metric or 3rd orders of the extrinsic curvature. So the point, the lessons that we learn from this this is that we can approximate the extrinsic space-time geodesic half square geodesic distance by defining 3 Taylor series in the intrinsic geodesic distance, and by that alone we only require 3 normal time derivatives of the metric. However, when we look at the coefficients of the Hadamard part of the Hadamard form, we find 4th order normal derivatives of the metric, and even the term v1 appears explicitly in the expression for the renormalized stationary tensor, and that's what I explained before, that we cannot take those higher order terms from this expression. However, we can use the semiclassical Einstein equation to determine, once we put all of these results back into the expression, the 4th order derivatives, for example, but we still need to specify up to 3rd order derivatives of the metric for reconstruction of the Hadamard condition in the hypersurface, which is, as I said, currently an approximate condition, but it allows to compute an exact expression for the energy momentum tensor. What we can now, what we do in the paper is to conjecture that if we require the solutions to be reduced to at least formally equivalent expressions for the classical solutions in the limit when h bar goes to 0, we will be able to implicitly solve also for the third time derivatives of the metric, and then we can begin construction the complete set of initial data for the higher order problem, so that the solutions constructed this way will be contiguous, so to say, continuous with the solution that goes that is defined by the limit where h bar goes to 0. As Bernard previously explained, these solutions in the h goes to 0 already include some special cases that are of interest. So that's all I'm going to talk right now. I think I've already
okay. Thank you very much for your interesting talk, which is the last talk of the workshop. So now it's time for questions. Okay, I see two questions. First, maybe Dan Jansen.
Yes, hi. Thanks for the talk. It was lovely. It was. I had a few. Well, again, the most important question for me is these approximate Hadamard states that you discussed. They seem to me very reminiscent of adiabatic Hadamard states to, let's say, the necessary order to calculate the stress energy tensor. Are they the same class of states, would you say, or is it a little bit more complicated?
I'm not sure. I'm not studied yet if they actually match some adiabatic Hadamard states, because I think this kind of approximation, at least in this exact form, has not been done. But I think it can be expected to be very similar to that.
Because I think for adiabatic states, you also only need a sort of finite number of time-like derivatives with respect to some. Yeah. So that's
I don't know. I don't know.
And can you say anything about, let's say, I mean, propagation of singularities for these states? So let's say I have a initial surface where my initial state satisfies these approximate Hadamard condition. Will it still satisfy that at some later time?
We can only conjecture that it will, because for that to happen, we will have actually the initial value problem to be well posed, right? Because
I mean, if you can relate them to adiabatic states, then you could use some Sobolev form, some of the propagation of singularities theorem, and maybe prove it like that. But I imagine,
but the issue here is that the space-time itself will not be granted to behave fine, right? Maybe,
but I'm just saying, let's say, I'm just talking about states on a fixed background at the moment. So
well, then it's yes, this kind of states should behave should propagate the singularities at least to a certain order.
Sobolev regularity. Yeah.
Propagated finally.
Okay, so thanks for your question. We have a second question from Stephen Fulling. So whenever you want.
Yes.
Okay, here I am. Sorry for the delay. I had to unmute. I'd like to ask you, or Daniel, or Bernard, if they want to jump in, a basic conceptual question. Why is there some reason for believing that the spontaneous state reduction should happen at discrete times rather than by some kind of continuous process?
I think I can answer that. No, not particularly, or at least not physically backed up. Essentially, we take this point because it's the simplest thing we can do. Of course, a continuous collapse scheme could be considered, but it's a little more complicated. So we are like in the order zero in this approach. So we are considering for the time being these discrete collapses. But we would actually like to relate this problem to a continuous scheme, and maybe it could be related to stochastic gravity and some kind of schemes of that type, of that kind. But no, there's no a particular physical